Okay, so this is from the Polymers and Giant Covalent section. If we look at the warm-up first, this is a relevant one this time, that we've got a series of compounds there, and it's asking us to circle the one which represents the giant covalent structure. Now, we can see fairly simply that the first diagram is of diamond, and that is a giant covalent substance. But if we just quickly run through the other ones as well, the second one is a polymer structure. Now that is a large covalent structure, but isn't necessarily regarded as a giant one because they are finite. They can go on for quite a long distance, so the N number can be quite large, but they do generally have a finite size at some point. The third diagram is a simple covalent substance, possibly something like ammonia, NH3. And the fourth diagram is an ionic one, because you can see the positive and negative charges in the substance. So the first one is a giant covalent structure, and that's specifically a diamond, which is mentioned in the first question actually, is that they are substances with very high melting points. And so which of the following compounds is not an example of a giant covalent structure? Well, obviously, a giant covalent structure will have a high melting point. That's one of the key ideas about what their structure allows them to have in terms of physical property. And so diamond and graphite themselves are probably not the answers to that question, which gives us two other possibilities, one of which is silicon dioxide, the other of which is ammonia. Now, ammonia we had already mentioned in the first question. It's potentially this structure here. And so whenever we have a small molecule, we generally have lower melting points because we are breaking not the covalent bond, but the weak intermolecular forces between it and another molecule of something alongside it rather than the actual covalent bond. So ammonia is probably the answer, or is the answer to this one. And the reason we also know silicon dioxide is the chemical name for sand, and actually, although not quite identical, it has a structure similar to diamond actually, with an SiO2 formula, but the silicons are arranged in a similar fashion to the carbons in diamond, which, if you remember the first diagram on the warm-up. So when we are melting a giant covalent compound, the covalent bonds between the atoms must be broken. Now this is different to, as we were talking about the small molecule, where we are breaking the weak intermolecular force of attraction. We're actually breaking a fundamental covalent bond this time. So for example, I've drawn not representatively, but if we are melting a piece of diamond which has got carbons bonded to lots of other carbons, etc., in a three-dimensional structure, we are actually trying to break these actual shared pairs of electrons, and a very fundamental thing requires us to say that covalent bonds are strong. And so if we are breaking something which is very strong, as covalent bonds are, lots of energy is required to do that. And so as a result, the high melting point comes out because you need a lot of energy to break those bonds. You're actually breaking real covalent bonds as opposed to intermolecular force of attraction, which are weak.